All right, we have started recording. I'll start the backup also. Okay, we are set. Let us begin. So yesterday at near the end of the class, I had started discussing about strain Rosette. We'll continue with those discussions today. This one. So I had mentioned that strain Rosette is basically a little device which is a combination of strain gauges, and these strain gauges are basically just thin wires which are pasted on a piece of paper or something, a very thin kind of like a band-aid kind of thing, which can be stuck onto any machine part or a machine component or anything. And as the machine part or whatever it is stuck on gets deformed, this metal foil or this metal wire, that also gets deformed. Deformed means it increases in length, maybe decreases a little bit in the cross-sectional area, and that leads to a change in its electrical resistance. And when it is connected to some kind of an electrical circuit, that change in resistance can actually be monitored. That can be monitored, that can be well calibrated, and through this indirect method of monitoring the resistance, the change in the length can be determined, and once the change in the length is determined, the normal strength, the normal strain can also be determined. So it's a very indirect way, but a very clean-cut way of and a clean-cut and a precise way of determining the strains. Now, as I was saying yesterday, that this is a very nice, sophisticated, I mean, it's a simple but sophisticated device of measuring the strain. But if you just use one strain gauge, it gives you just the value of the normal strain along a particular direction. For example, if you stick your strain gauge in like this, or you stick your strain gauge like this, individually, they will give you the normal strains along the directions in which they are stuck. The complete picture of the state of strain at a particular point in the body. Then what? Well, then there's a very simple way, which is to use this strain Rosette, which is a combination of strain gauges. So just like you can see simultaneously two strain gauges present here, you can have another strain gauge present here. And sorry about the bad drawing here. I mean, it does not overflow the actual body. Okay, it is very much stuck within on the surface of the body. So you have three strain gauges. So it's something like this. You can have a strain gauge like this. You can have another strain gauge which is at a certain angle to the first one, and you can have a third strain gauge which is at a certain angle to the first and the second one. Okay, you will be able to measure the value of the normal strain along this strain gauge. You will be able to measure the value of the normal strain using this strain gauge, and you'll be able to measure the value of the normal strain along this strain gauges. So the values that you will obtain from your strain Rosette, okay, so these three strain gauges together is the strain Rosette. The readings that you will obtain from the strain Rosette are just three values. Those three values, so suppose we say that this is strain gauge A, this is strain gauge B, and this is strain gauge C. The values that you are going to obtain from the strain Rosette are these values: the normal strain epsilon A, the normal strain epsilon B, and the normal strain epsilon C. Question is that from this information of just these three values, how can we determine the complete picture regarding the state of strain at that point? So any ideas? If you have already read the book or know it from some other resource, please try not to answer. But if you are just looking at it, hearing it afresh, try to think about it in a proactive fashion and give me some idea how I might go about trying to determine the state of strain at that point using these three values.
So based on the angle between those three strain gauges, we'll use the strain transformation, like along the epsilon xx, epsilon yy, and epsilon xy.
Yes, something like that. So what we do is we imagine that our x-axis is lying like this. We imagine that our y-axis is lying like this. This is x, this is y. Now, from this very picture, it is immediately clear to us that the value of epsilon a, it coincides, or that itself is the value of the epsilon xx. So there is no doubt about it. Similarly, from this particular configuration of the arrangement of this strain gauges, it is immediately clear to us that epsilon yy will be nothing but epsilon c. But what about epsilon b? What is it? So instead of thinking very specifically about these things, what we can say is that epsilon a, it will be connected, or it will be related to the strains epsilon xx, epsilon yy, and the gamma xy that will be associated with this x and y through the strain transformation relations. Because each of these strain gauges giving the values of epsilon a, epsilon b, and epsilon c, they are nothing but the normal strains, and we already know the formulas for the normal strains. So what I will do is I'll just write down these formula which we had written yesterday. So if you just go back, we had written this this formula for the epsilon x dash x dash. Okay, so it was in this form. I had written this in terms of the cos 2 theta and the sin 2 theta just to make it match with our textbook. But you understand that when you first do this calculation, it will come out in terms of the cos square theta, sin square theta. In fact, one of you was telling me the answer in terms of cos square theta, sin square theta. Similarly, for epsilon y dash is the same thing. So what we will do is we will think of each of those epsilon a, epsilon b, epsilon c individually to be like this epsilon x dash x dash. The only thing that is varying with respect to the x-axis is the value of this angle theta. So if we come back to this, for the first case of epsilon a, the value of theta is simply 0. For b, if you think that this angle is, suppose this angle is, we'll say now that this is theta b, but a very common configuration is where this theta b is equal to 45 degrees. And in this particular case, epsilon c will be 90 degrees. So with this information, we can write down the general relations, something like this. Please note I have written this in terms of the cos square theta a. You can easily convert this to the twice theta a, no problem. This is the general formula. The only thing that I have done is to replace the theta with theta a. Similarly here, we'll have the exact same formula, but this time I will have theta b. And for epsilon c, I will have epsilon xx cos square theta c plus epsilon yy sin square theta c plus twice epsilon xy sin theta c cos theta c. You see, we have these three equations in the form of three linear simultaneous equations where the unknowns are what? Tell me, what are the unknowns here?
Sir, epsilon xx, epsilon y, and epsilon y.
Right. So in these three equations, so we say that these are linear simultaneous equations with unknowns epsilon xx, epsilon yy, and epsilon xy. The good thing about this is these three equations, sorry, my writing app just crashed again. So I found this. Okay, so we have these three linear simultaneous equations with unknowns epsilon xx, epsilon yy, and epsilon xy. And the good thing here is that once we know about epsilon xx, epsilon yy, and epsilon xy, the complete information about the state of strain at this point is known. Okay, and once that is known, if you wish to determine the strain, the normal strain along any other direction, which is not along this, not along this, not along this, rather maybe somewhat along this, or maybe somewhat along this, someone along this, it is very easy to determine that, again by the application of the same kind of formula. Not just the normal strain, with the information in your hand of these values, you can also determine the gamma xy or the gamma x dash y dash about considering any two perpendicular lines. That is why instead of using one strain gauge, it is much better to use this combination of strain gauges, which is why the use of this strain rosette is so much widespread. And you will, in time you will also get to see some, get some familiarity with strain rosette as part of your lab. Had you been here, you would have been able to actually see it for yourself, but this is what it is. All right. So as far as the theory part is concerned, we are more or less done. We can go on to the solution of problems. I just want to point out something which I may not have emphasized that much yesterday. If we go back here, you see we were talking about the principal strains. I did not talk about the maximum value of the shear strain. So please tell me, what is the maximum value of the shear strain? I'll just write it here.
So,
please tell me.
Sir, epsilon P1 minus epsilon P2 by 2.
So it's like this. So gamma max, okay, so that will be actually twice R. Okay, I think it will be better if we, if you remember that this gamma is equal to twice epsilon. Okay, maybe it will be better if I just replace this thing. This is not actually gamma. This should be epsilon. Sorry, I mean to say that this is epsilon normal. This is the epsilon xy. So it's better to write this as gamma by 2. Okay, this axis, that is the epsilon xy thing that I'm thinking about, the shear strain that I'm thinking about. Okay, but you remember that gamma is equal to twice epsilon, so we may as well write it clearly as gamma by 2. Okay, then it will be clear. So this gamma max will be twice R. Okay, but remember that this gamma max, the maximum value of the shearing strain, this is actually the in-plane maximum value of the shearing strain. Meaning to say that if you compare with the corresponding discussion in the context of stresses, you have seen that when we are concerned with one particular plane, you were able to find out the tau max in plane. There were a number of problems also in the tutorial sheet. But when you considered the total three-dimensional state of stress, you ended up with 3 more circles, and you had a different value of the absolute value of the shear stress. In a similar fashion, the in-plane shear strain maximum value will be different from the absolute maximum value of the shearing strain. So in a general three-dimensional state of strain, you will have to find out all the 3 different values of this principal strains. So you please note that this twice R is equal to epsilon P1 minus epsilon P2, the absolute value of that. In 3D, the absolute gamma max, the gamma max absolute will be the maximum value of these things. Sorry, this one, this one, this one. It will be the maximum of all three values. So you calculate one value considering two of the principal strains. You calculate another value considering two of the principal strains. You calculate another value considering two of the principal strains. The maximum of all, considering all these three, that will be the absolute maximum value of the shearing strain. And of course, if like you had done in the case of the 3D stresses, if you arrange these principal strains in decreasing order, like epsilon P1, epsilon P2, and epsilon P3, then there is no doubt that the maximum absolute value of the gamma max will be epsilon P1 minus epsilon P3, that thing. Okay, so when you are reading a question, you please take a note if it has been explicitly mentioned whether it is a maximum in plane value of the shear strain that is being asked, or the total or the overall maximum value that is being asked. Okay. All right, I just wanted to point this out. We can go on to the problems now. I had asked you all to try to attempt problems 1, 2, and 5. Those were at least question numbers 1 and 2 are mostly like plug and play kind of thing. You just have to substitute the proper values in the formula and get the thing. In fact, most of these problems are like that. Maybe 1 or 2 are a little bit different, but have you tried that?
Yes, sir.
And are you getting the answers for question numbers 1 and 2?
Yes, sir, I got them.
Okay. Anyone else?
So I did not try.
Then do try. Please do try.
Yes, sir.
Yeah. Has anyone else tried and maybe gotten partial answers? Maybe some parts they're getting, some parts they're not getting, because those are dangerous situations. For question number 1 and 2, I'm asking. Okay. 5 is a little bit different. If you have not tried, please do try, because these are kind of repetitive problems. You just have to put in the values correctly, find out the principal strains, find out the angles of the principal strains. Very straightforward, but suppose, I mean, I said these as questions in the assignment or the test. Very straightforward things, but you do have to do the calculation correctly to get the marks. Okay. So I hope you will do a little bit of practice. You can use your calculator by all means, but I personally find it much easier if I just write up one code and utilize that code repeatedly. All right. Anyway, let's go to the to this problem, which is involving a strain rosette. So the strain rosette is attached to point A on the surface of the support. So there is some kind of an engineering structure here. There is a support here, and at one point on this support, the point A, one strain gauge is attached. And as you can see from the scale of this picture, the entire strain rosette just looks like a dot from a certain distance. Only when you zoom into it, you will be able to see its proper configuration like this. Please note that unlike the example which I had drawn in the previous page, this here is having a certain different kind of orientation, which is why I have chosen to demonstrate this. So again, this epsilon A, epsilon B, and epsilon C values are given. The only thing where you have to do a little bit of brain work here is to identify what are the values of theta A, theta B, and theta C. So tell me, if you can write that out, everything else is just follows very algorithmically. Just step by step, you have to do the calculations properly. So tell me, what is theta A?
0, 60, and 120.
Okay, so theta B is equal to 60 degrees. So theta B should not be a problem. I mean, it's quite obvious that theta, so this epsilon, The strain gauge A is lying along the x-axis. So the angle between the strain gauge A and the x-axis is of course 0 degrees. The angle between the strain gauge B and the x-axis is 60 degrees. What is the theta C? Tell me.
Sir, is it 120?
Yes, it is 120 degrees. Okay, you see that the angle that this strain gauge C is making with the x-axis is given as 60 degrees, but it is on the along the negative direction of the x-axis. So we are calculating our angles. If we go back to the previous thing, we were calculating our angles from this positive direction. Okay, so this is theta B, and you understand that this is theta C. Okay, it's like this. This is theta B, this is theta C. So theta C here is 120 degrees. So you can just replace the values that we have. I mean, the same kind of thing that we have done, you can do it and obtain the values of obtain the values of epsilon xx, epsilon yy, and epsilon xy. Okay, this can be immediately found out by solving those three linear simultaneous equations. Next, it has been asked, determine the in-plane principal strains. I mean, it's very straightforward. You just have to go back to these formulae that we have written earlier, find out the average value, find out the radius like this, and then you just have to use this thing to find out the two different values of the principal strains. All right, and for the principal strain orientations, which has also been asked, I believe, the next question, that is what it is. Okay, the next question is the maximum in-plane shear strain. So I've just told you about that. The gamma max will be equal to twice of R. Again, just a plug and play kind of exercise. The average normal strain associated with the maximum in-plane shear strain. So tell me about this. Little bit of brain work is involved here. The average normal strain associated with the maximum in-plane shear strain. What is that? What are the normal strains?
Sir, epsilon xx, epsilon yy, and epsilon xy.
Right. Not epsilon xy. The normal strains are epsilon xx and epsilon yy. Okay. Now you go back to this Mohr circle kind of picture. You see here, where is the maximum value of, or in this picture, the point which is corresponding to the maximum value of this gamma max. It is here. Is it not? This is gamma max by 2. But this is the point where it is occurring. So what are the normal strains associated with this point? It's here. This is the normal strain. If you just drop a perpendicular. And what is that value? This is the average. And that is the average. That is what has been asked here. Okay. So what do you think the value will be? Is it epsilon xx plus epsilon yy by 2, or is it going to be epsilon p1 plus epsilon p1 by 2, or is it going to be something else?
So epsilon p1 plus epsilon p2 by 2.
Anybody has any other opinion? So my question is, I'll give you a multiple choice question. Answer is epsilon x. Let me not write it here. So for the part C of the question, my question is that whether that answer is epsilon xx plus epsilon yy by 2, or is it epsilon p1 plus epsilon p2 by 2.
Both are same.
Yes, you'd think that these two things are the same. Okay, but hold that thought. Okay, hold that thought. The thing is not so straightforward. The reason why some of you may be thinking that this must be same is that back in when considering stresses, we had talked about something called the first stress invariant, and there we had said that things like this, that sigma xx plus sigma yy by 2, that is, or just this particular combination, this is invariant, whether you take it in the xy coordinate system or the xy or the x dash y dash coordinate system, or the principal stresses, these are all the same. Okay, but please note that here I am writing, so in a very similar way, you may be tempted to think that this average value is going to be absolutely equal to this average value, and so on and so forth. Okay, but don't just jump to conclusion immediately. Okay, there are a few other things to consider here also. So I don't want to discuss it right away. I want to discuss a few other things and then I want to come back to it. Okay, so just hold your thought. So we'll come back to this. Finally, it has been asked, specify the orientation of each element that has these states of strain with respect to the x-axis. So for the principal strains, the angle will be given by this thing. Tell me what should be the formula for this. Look back at what you had written for the stresses. Same formula, just replace the sigma by the epsilon.
So 2 epsilon xy by epsilon xx minus epsilon x by y.
Exactly. As simple as that. Okay. So from this you will be able to get two different values of this theta p. Okay, it's as simple as just taking the tan inverse of this value. You just plug in the values here, take the tan inverse of that, take the half of that, just convert radians to degrees, you will have the answer. Of course, if you do by calculator, I don't know, I mean, if your calculator gives two different values of the theta p or not. If you write it in Python, you will get a single value. Single value means that you will get the theta p as something like 11.705, something like that. Okay, degrees, which is why this is 11.7 degrees. Now, this is one value of the theta p. The other value will be simply theta p1 plus 90 degrees. Okay, you don't even have to use Python or any calculator for this. It is that because whenever tan 2 theta p has a certain value, you understand that tan, I mean, the 180 degree plus this twice theta p is also having the same value. Okay, which means that the other angle is theta p plus 90 degree. If it is, if 2 theta p and 180 degree plus 2 theta p is the same value, then it means that theta p and theta p plus 90 degree have the same values. Okay, it's like that. You know all these things from your high school trigonometry. What about the shear stress? Sorry, the shear strain angle. What is the value for that? Tell me. What is the expression for that rather?
Epsilon xx minus epsilon yy by 2 epsilon xy.
Say that again, please.
Sir, epsilon yy minus epsilon xx by 2.
So the first answer was wrong. So it should be, so let me write that explicitly. So you have to take the inverse of this, but with a negative sign. Again, I am writing down these formulas just by taking a direct analogy with what we had written in the case of the in-plane shear stress. You go back and check that formula. I had also mentioned that tan 2 theta p into or multiplied with tan 2 theta s, that is going to be equal to minus of 1. Okay, so this is what it is. And from this again, you will be able to find the values of theta s. That's it. So we'll come back to this question. Let me go on. Let me move on to some of the other problems and then we can come back. Okay, let's do this. So we have a cantilever beam here, which is on which there is some kind of a tip load being applied. The strain in the x direction at the point A on the structural steel beam, Young's modulus and shear modulus are given. So the strain in the x direction is measured and this value is given as 100 microns. 100 microns means, so in the previous problem also, all these answers, these are given as 336 mu. Mu means it's like 336 into 10 to the power minus 6. And yesterday, mind you, I had told you that the values of the strains, they usually come out in the form of 10 to the power minus 4. So this is like that. Okay, you see that this is 3.36 into 10 to the power minus 4. Similarly, this is 536 mu. So it is 5.36 into 10 to the power minus 4. Similarly, the others. The same kind of things is mentioned here. So epsilon xx is 10 to the power minus 4 basically here. Determine the applied load P. Okay, so a certain twist has been given to this problem, and what is the shear strain at gamma xy at point A. So tell me, how should I proceed here? Epsilon xx is the only thing that is given to us. This we know. From this, what can we extract? We have to find out, see, you work backwards a little bit. Determine the applied load P. Okay, what is the connection between this P and this point A? Think about it. Because see, in none of the formulas that we were discussing, either in the context of the transformation of stress or in the context of the transformation of strain, there was any mention of any load. In fact, I told you that we are basically talking about kinematics here, especially in the transformation of strain. We were not saying, okay, this load is happening, that load is happening, nothing of that sort. And suddenly we have been asked here to find out the load. So what is going on? We have to use something else.
So because of that load P, we will get sigma xx and all the stress components at point A.
How do you get that? So because of P, you will get some sigma xx. What is that relation? You don't have to give me the formula, just explain.
So we consider the bending moment
Exactly.
due to the
that is the word.
P.
Yeah, that is the thing. So because of the application of this load P, you will have a distribution of shear force along this beam. You will also have a distribution of bending moment along this beam. So this was very much part of your assignment 1 syllabus and your test 1 syllabus. So anywhere along this beam, you can find out the shear force and the bending moment. Now, the moment you have the bending moment, you can find out the flexural stress or the bending stress at any point. So we work backwards like that. That P, it gives rise to bending moment. Bending moment gives rise to flexural stress or bending stress. So this formula is sigma is equal to my by I. I'm not considering any minus plus here. It's just the magnitude I'm talking about here. So this is my by I. This m will be obtained from P. So the expression of m will involve the P. That you understand. Okay, it will be some this distance or whatever, however you want to calculate this, P times 1.2. This will be something like that. Now, how do you make the connection between this sigma and this epsilon?
So Young's modulus is given.
Yes. So sigma will be equal to E times epsilon xx. The reason that I am writing like this is that because within the restrictive assumptions and the simplifications associated with this Euler-Bernoulli beam theory that we're working with, you will not have the presence of sigma yy or sigma zz. You will only have this connection. So what we are effectively writing is this. Epsilon xx is equal to 1 by E sigma xx minus nu sigma yy plus sigma zz. But sigma yy is 0, sigma zz is 0. That is why epsilon x6 is equal to 1 by e sigma x6, and that is why this sigma x6 is equal to e times epsilon x6. So now you have this thing where on the left hand side you have this my by I. Mind you that the value of the y can be easily found out because the distance of this or the position of this point A has been very well given to us. You can see here within this cross section, the distance of the point A from the top edge that has been given as 50 millimeters. So we know this complete information. This is a simple rectangular cross section. So I will be 1 by 12 BH cube. You know this, you have done this many times. M is also known dependent on P. So this entire left hand side can be written in terms of the P, and everything else is a known quantity. On the right hand side, you have the value of this Young's modulus. Epsilon value is also given to us. Okay, this is known to us, 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 and this comes out in terms of P. So P times something. So within that bracket, whatever is there, that is known to us. So everything is known. So you can find out the value of P. So the first part of the question, determine the applied load P. I've told you how to go about doing it. Next, you tell me what is the shear strain gamma xy at point A. How do we go about doing that?
Sir, there will be a shear stress at the section where A is cut. So from that we'll find the tau xy at that point, and from that we'll go.
Okay, we can find out the tau xy value at this point A. What is the formula for that?
VQ by IT.
V into Q divided by I into width.
Yes. So VQ by IT. What is the value of this V? V is the shear force at that particular cut section. What is V?
It will be equal to P.
It will be equal to P for this cantilever beam, because if you make a cut section here, the exposed surface there, that will be having the simple value of P. Okay, so through a simple force balance. So this is P. How will you find out Q?
Sir, it's first moment of area.
Exactly. So Q is the first moment of area corresponding to the position of this A. So our rectangle is like this. Our A is somewhere here. So the point or the part of the cross section which will be of concern to us will be this part. Okay, alternatively, you can think of it as the lower part also, but then you'll have to do the calculation from the bottom. Okay, if you take this part, you'll have to do the calculation from the top. If you take the bottom part, you have to take the calculation from the bottom. Either way works, you'll get the same value. I is I, 1 by 12 BH cube. T is again equal to B. So everything is known here. Now, how do you find out this gamma xy?
So we know gamma xy is 2 times of epsilon xy, and to find epsilon xy we use that rigidity modulus G.
Exactly. So gamma xy is equal to twice of epsilon xy, and epsilon xy, that will be what? Tau xy divided by twice G. Okay, G value is given to us, 2 and 2 cancels. So this is gamma xy is simply tau xy by G. Tau xy value you have just found out because P you have already found out in the previous part of the problem. Okay, so from this you can find out the gamma xy also. That's the route you have to take. So I hope this is clear to everyone. Any questions regarding this?
Sir, can you please repeat why you cancelled? I mean, how did we get 2G in the denominator?
Which one?
We got 2G in the denominator for epsilon xy.
Yeah, so tau xy is equal to twice G epsilon xy. No? That's why.
Okay, sir. Yes, sir.
Is it not?
Okay, sir. Yes, sir.
It's a
I
simple,
recall it.
yeah, from BM. You just revise your notes from BM. You'll see. Okay. Next up is this one. So deduce that in the case of plane strain, okay, mind you, plane strain, for a body made of a material that follows the generalized Hooke's law, the stress component sigma zz itself is a principal stress. It's a very innocent looking question, and there is not much to do here in terms of calculations or anything, but there is something to think about here. So what we are talking about here is a case of plane strain, and that plane strain is occurring in that xy plane. So just like we have developed our theory. And this plane strain is occurring in what kind of a body? It is occurring in a kind of body where the material is following Hooke's law, generalized Hooke's law. Okay, so plane strain means that we have epsilon zz equal to 0, epsilon yz equal to 0, and epsilon zx equal to 0. So the moment you see this plane strain occurring in the xy plane, you can immediately write this thing with full confidence. Next, from this, what can we say about the sigma zz? What can we say about the sigma zx? What can we say about the sigma yz or the tau y? So first of all, let me write this tau yz, that is equal to twice g epsilon yz. Since epsilon yz is 0, tau yz is coming out as 0. Tau zx is equal to twice g epsilon zx. Since epsilon zx is 0, tau zx is also equal to 0. Now sigma zz, what about this? Well, you see, we have this expression from the generalized Hooke's law that epsilon zz is equal to 1 by e sigma zz minus nu sigma xx plus sigma yy. Now this sigma xx, in general, it is not going to be equal to 0. This is not going to be equal to 0. This looks weird the way that I have written it, sorry. Okay, so this thing is not equal to 0. This thing is not equal to 0. However, this epsilon zz is equal to 0 because we are considering plane strain, which means that sigma zz is not equal to 0. Now you see the situation. You have the xy plane, something like this, okay? You have the xy plane, something like this. This is our x, this is our y, and our z is like this. So the normal stress along the sigma z, along the z, that is the sigma zz, that is coming out as non-zero. But on this plane, the shearing strains tau yz and tau zx are coming out as 0. What is the indication here? The indication here is that the sigma zz, that itself is the principal stress. And that is what has been asked. So we have to deduce that. So the only real thing that we had to do was to identify that the shear stresses are 0. That follows directly from from the strain components, from the shear strain components, and the sigma zz is not 0. The moment you identify that thing, you are good. In fact, okay, here it is coming out that sigma zz in general it is not equal to 0. But suppose in some particular situation sigma zz also comes out to be 0, then also it is true that that 0 value of sigma zz is one of the principal stress values. Please make particular note of this. As long as on a particular plane the shear stresses are 0, even if the sigma zz value there is 0, that itself is a principal stress. Okay, in general it will not be equal to 0, but coincidentally in some problem if it is coming out to be 0, let it be so, that will be a principal stress. So in the case of plane strain we have this situation. Okay, so does anyone have any doubt about this? It's a very subtle concept. Many students make this mistake. I mean, in the third or fourth week of October, we are going to have the comprehensive or the grand viva of the fourth year students. So we are all getting into that mood of asking these kinds of fundamental conceptual questions. So maybe one day we'll also get to face these things. So if anyone has any problem with this, please let me know. Many students have very, I mean, a confused understanding of plane strain and plane stresses, which is rather unfortunate. Okay, which is why I am emphasizing on this so much. Okay, let's go next. For a material that behaves according to the generalized Hooke's law, again, we will consider this case of plane stress. Fine. And derive the strain transformation equations from the stress transformation equations. All right. So this derivation part that may involve 3-4 lines, or maybe even 5-6 lines, doesn't matter. But what I am actually interested in is in this part B of the problem. Okay, but just for the sake of completeness, you tell me how should I go about doing this first one, considering the case of plane stress in the XY plane. So you understand that for plane stress, I will have, so plane stress along the XY plane, sigma ZZ is equal to 0, tau ZX is equal to 0, and tau YZ is equal to 0. And we have been asked to obtain from the stress transformation equations the strain transformation equations. So the stress transformation equations for plane stress that we already know. So sigma x dash is equal to sigma xx cos squared theta plus sigma yy sine squared theta plus 2 tau xy sine theta cos theta. This is the thing. You will have a corresponding expression for sigma y dash also, where you will just replace this theta by theta plus 90 degrees. What you have to do is, from this thing, you have to obtain the strain transformation equations. So you have to convert from this directly to the epsilon parts. And the way that you go about doing it is to consider these things, that epsilon xx is equal to 1 by e sigma xx minus nu sigma yy plus sigma zz. The immediate simplification that you can observe here is that this sigma zz is equal to 0. Next, epsilon yy is equal to 1 by e sigma yy minus nu sigma xx plus sigma zz. This sigma zz is again 0. So you have this simpler expressions. And from these two equations, okay, you should be able to express the sigma xx and the sigma yy in terms of the, so as some functions of epsilon xx and epsilon yy. Here also some function of epsilon xx and epsilon yy. All right, it will come out something like e times epsilon xx plus nu epsilon yy by 1 minus nu square. Similarly, this one will come out as e into epsilon yy plus nu into epsilon xx by 1 minus nu square, something like that. Now, once you obtain those things, you can also obtain from this sigma x dash the corresponding epsilon x dash. Once you replace all of these things and solve for the epsilon x dash, epsilon y dash, you will be able to obtain absolutely the same kind of things. Okay, so as long as you understand that the body is, or the body material is following the generalized Hooke's law, then from the consideration of the stress transformation equations, you can obtain the strain transformation equations. That is what has been asked here. Okay, that you can do. So you will obtain after doing this simplifications that epsilon x dash is equal to the usual business. Okay, that will easily obtain. This is what you are supposed to obtain. Okay, this is just algebra. I'm not so so we'll obtain this thing. But what I want to discuss is this part B of the problem, where you have to think a little bit. How does the strain component epsilon zz transform in this part A? Because the formula that you will obtain is for epsilon x dash and epsilon y dash, maybe even for epsilon x dash y dash. But the epsilon zz is remaining. And please note that this is a case of plane stress. All right. So for plane stress, is it true that epsilon zz is equal to 0 or epsilon zz is not equal to 0 generally? Tell me, for plane stress.
Non-zero.
Non-zero. So epsilon zz is equal to 1 by E sigma zz minus nu sigma xx plus sigma yy. This sigma zz is 0, fine. But still epsilon zz is equal to minus nu by E sigma xx plus sigma yy. In general, neither this sigma xx nor this sigma yy nor this combination will be equal to 0 in general, which means that epsilon zz is not equal to 0. But the question is, how does it transform? Epsilon zz we have found out, but do we actually need to go for epsilon z dash, or is it the same thing?
Sir, epsilon z dash will be same as epsilon z.
Exactly. So yeah, observe. It's just a one-line thing, okay? So you just observe that epsilon zz and this thing is the same as epsilon zz. It's exactly the same thing. Now I have extended this problem to the plane strain. So reverse the tables now. So consider the case of plane strain. So when you consider plane strain, instead of this sigma zz, tau zx and tau yz, you will have epsilon zz equal to 0, epsilon zx equal to 0 and epsilon yz equal to 0. So from that, now you start from the strain transformation equation. So that is what has been asked. Derive the stress transformation equations from the strain transformation equations. You start from the strain transformation equations, and from that, just like here we obtain the strain transformation equations from the stress, you do the reverse thing now. Okay, slightly different algebra, but the spirit is the same. So part C follows almost exactly like part A. What about part D? How does the stress component sigma zz transform in part C? So tell me about this part D. You just note that sigma zz is not equal to 0. Okay, and observe that sigma z dash will coincide with sigma zz. Now I notice that I have run out of time, but I wanted to go back to this problem that I had left earlier. That strain Rosette problem. This one I wanted to come back to, but I will discuss this in the discussion channel. Okay, so please keep your eyes open for that discussion. Okay, so class is ending now. Somebody had pointed out yesterday that I should be leaving the class a little bit earlier so that there is some gap with the next class. So we end it here. Okay, thank you very much, everyone. Please go to your next class. Take a couple of minutes break and go to the next class.
Sir, excuse me, sir.
Yes. So class has ended. Okay, so everyone please leave. Yeah, tell me.
Sir, yesterday while discussing the strain Rosette, so you said that we'll be using 3 or 4 strain gauges. So if we use 3 strain gauges, we are getting all the epsilon xx, epsilon yy and epsilon yz.
Right.
XY, why are we using another strain gauge in practical purpose?
So the fourth strain gauge mathematically is redundant. Okay, you are absolutely right. The fourth strain rosette, the fourth gauge in a strain rosette is mathematically redundant. You don't need that to obtain the values of epsilon xx, epsilon yy. But what can happen is that suppose let's say that you have that this kind of a configuration. Okay, so epsilon and this a is along the x-axis. You have the b at 60 degrees and the c at 120 degrees. Suppose you are interested in directly reading out the strain gauge value in a direction perpendicular to the x. So you can stick another one. Okay, so instead of obtaining through calculations the value of that normal strain value in the perpendicular direction to x, if you just stick a strain gauge here, it's redundant mathematically, but if you stick it here, you can directly read out the value of the epsilon yy. That's the only thing. Just for convenience.
Yes, sir, got it. Thank you, sir.
Yeah. Thank you, sir.
Excuse me, sir.
Yes.
So actually, I'm not able to understand that how the triangle is there at the point A, sir. So means
Also, what is there?
so that point A, so in question number 4,
Yes, yes, sir.
it is like triangle means A, B, C. So
Yes.
means how it is such small in practical purpose.
Oh, you mean how is it stuck there?
Yeah.
So, I mean, usually they take a piece of paper or something. Of course, it's a sophisticated piece of paper, and they stick this strain gauges like that. You can buy these things actually. I told you, it's like a piece of band-aid. So it's like this. And wires are coming out of this so that you can connect it to some kind of electrical circuit. So this thing, just like a band-aid, you can put on a machine part. Just stick it there.
So actually, I have one doubt.
Yeah.
So actually, basic principle of this thing is like that resistance is proportional to length. But
Yes.
sir, in when we means in use when while using potentiometer, we get a lot of errors. Means end error like that. So will it not give? It should not give correct.
No, no.
Means
See, when you carry out your experiments in electrical technology, you are setting up those things, right? You are setting up the wires and everything. You are not going to sell those things. It's not a commercial enterprise there. But people who sell these strain gauges, that is their business. Okay, they have invested a lot of time, money, and research into making just these three pieces, which will not give humongous errors. Okay, it will always give errors because it's after all a practical experimental thing. It will always give errors, but not the kind of errors which you are prone to seeing in your electrical technology lab work. Okay,
so
so
that's why I was confused because
no,
the
there is a
straight.
there's a bit of difference between what you do in your lab and when people actually fabricate these things in a professional way and sell it to earn money.
Okay, sir, got it now.
Otherwise, you see, if that had been so simple, every Tom, Dick, and Harry would have just stuck together three strain gauges. I mean, I can also put Fevicol and put a strain gauge on a piece of paper and sell it. Will it work?
No, sir.
And then try to understand that.
Yes, sir. Thank you, sir.